Hi there. So I'm going to show you how to do questions C and D on page 30 and 31, I think, of the ISA. So let's start with this one here. Figure out how to use this. There. Okay. So we're going to assign oxidation state. Sulfur is -2. Lead has to be +2. This is hydrogen peroxide. So in a peroxide oxygen, each individual oxygen has a charge of -1. There are 2 of them, so -2 total. And these hydrogens are 2. Okay, sulfate's charge is -2, so this must have an equivalent amount of positive charge. And then if we go inside, oxygen is 4 times -2, -8. And then to make the whole sulfate add up to -2, this has to be +6. -2 here for oxygen, 2 times +1. So we want to scan the reaction to see what has changed. And we can see that the sulfur has changed here from -2 to +6. So the first thing we want to do is check that it doesn't appear anywhere else, and it doesn't. And then also check that it's balanced, which it is, 1, 1. So now I can do the number of electrons. So -2 to 6, that's becoming increasingly more positively charged. So it's oxidation. And -2 to 0 would be 2 electrons, and then up to 6 would be another 6 electrons. So this is 8 electrons lost. Now, here we have oxygen. Hydrogen is +1, +1, so that's not changing, so it's the oxygen. But the oxygen has changed here. It's -2, and here, -2. So we need to figure out how many electrons that oxygen is transferring. So to do that, you just want to compare to one of these. It doesn't matter which one really, because it's -2. And because it's in 2 places, we don't transfer the coefficient that we're going to multiply the electrons lost to make them equal to electrons gained to the right side, because that oxygen, that amount of oxygen is divided amongst these things. And so we have to make sure that the combined numbers add up to what we want. So I'm just going to compare to the water here. And I choose the water to make my decision about how many electrons, because the lead sulfate is already paired with lead sulfide, and that's going to get me the right coefficient in front of that substance, because I'm balancing the sulfur because it's been changed. So I don't want to touch that. It's just complicate my life if I do. So I'm going to check with connect to the water. Okay. So while it's -2 in either compound here, and I could technically use either one to figure out the number of electrons, I'm going to be smart about my choice and compare it to something that's not involved elsewhere, because that would just make it harder to keep track of everything that's going on if 2 things are changing, the sulfur and the oxygen. So I'm going to compare to the water. I see that each oxygen goes from -1 to -2. Remember to balance by putting a 2 here, because there's 2 oxygens on that side and 1 on that side. And so -1 to -2 is 1 electron. But with 2 oxygens doing that, a 2 goes there. Okay? So now I'm going to balance the number of electrons lost and gained by multiplying by 4. And typically, in a typical straightforward problem, the 4 would go here, and then you would transfer to this side too. We can't do that because, remember, some of the oxygen is in the water that's been reduced, and some of it is in the sulfate. So then it's really, we're balancing it correctly on the reactant side, but we wouldn't get the right number on the product side because it's in 2 places. So I'm going to leave that and not transfer that 4, because I'll likely have to change it anyway. And I'm going to just do this side by inspection, which I can safely do because I know that all the oxygen is in the peroxide, and I know the number of that. It's 4. And so 4 times 2 is 8 O's on that side. So I know that now that other side has to add up to 8. And because I've already balanced the sulfur, I know that the coefficient in front of the lead sulfate is fine. So I just have to adjust this coefficient. And so I do that by saying, okay, I need to have 8 oxygens. I have 4 here, so that has to become a 4. So there's a small little adjustment there. Okay. Okay. So now, going to the second one here. If I can move this. Down. Oh, there. Okay. So let's assign oxidation states here. So aluminum is 0, and then aluminum is +3 here. And this whole thing has a charge of -1, which makes sense because hydroxide is -1 individually. 4 of them would be -4, with +3 leaves a -1. Let's do the inside, +1 here, -2 there, 0 for that hydrogen, -2 times +1 here, and then +1, -2 there. Okay, so I can see that the, choose a different color, the aluminum is changing, and so aluminum is going from 0 to +3. It's already balanced, so you don't have to do a pre-balancing, so this is 3 electrons lost. Okay, so now again we see that oxygen is the same on both sides, but hydrogen is +1 here, +1 here, and 0 there. There's also some hydrogen there that's +1. So some of the hydrogen is not changed. It's not being oxidized or reduced, but some of it is being reduced. So the portion that ends up in H2 here is reduced. So we're going to connect the H2 to one of these, either this one or this one. It actually does not matter who you connect to, you'll get to the same answer, okay? So I'm going to connect to the hydroxide, but it really does not matter if you connect to the water. And so I see right away that if I connect to the hydroxide, that the hydrogen is not balanced. So I need to put a coefficient of 2 there. Now I know that it's going from +1 to 0, that's 1 electron, but times 2 for all the electrons, so that's 2 electrons. So this needs to be multiplied by 3, and this needs to be multiplied by 2. We transfer the 2 here, we transfer the 2 here, and now the 3 we're not going to transfer to this reactant side because remember that some of the hydrogen is +1 in the water and some in the hydroxide. So that side is best to do by inspection, but we can transfer it here because that's where it's changed. Okay, so now we have the numbers on the product side. And so we can use those numbers to help us find the remaining number, which is here in front of water, by inspection. So on the right side, we have 2 times 4, so 8 O's. Okay, so that would mean to get 8 O's, remember that I have 2 O's here, so that accounts for 2. So I would need this coefficient to be something that would add up to 2 to get 8, so 6. Okay. That should balance the hydrogen if everything is done correctly. 3 times 2 is 6 for hydrogen. 2 times 4 is 8, so that's 14. So hydrogen on this side is 12, 13, 14, so it checks out. So all done. Now, if you want to check your reaction to make sure that it's completely balanced, you should check more than just the number of atoms, as well, I didn't go back and redo it, but you can check the number of atoms and you can also check the charge. So let's check the charge on the left side and right side to make sure that they're the same. So on the left side, I have a -2 overall charge. And on the right side, 2 times this -1 is -2. So I'm feeling pretty good because the left side equals the right side. Okay. Now, if you're worried that I picked hydroxide here, and why couldn't I have done starting with water, maybe I'll show you how it doesn't change anything, okay? Might make it a little tad harder to balance, but I can show you a trick to fix that, to make that easier. So I'm just going to run through that. So just erase this. Okay, so aluminum plus hydroxide and water goes to AlOH, 4 -1 plus H2. So we know that this is 0 and this is +1. I'm not going to fill in all the oxidation states. And then the aluminum is 0 plus 3. So we knew that this was 3 electrons lost. Okay, so now instead of connecting to the hydroxide, I'll show you how it doesn't matter. We'll connect there. So there are 2 hydrogens, it's balanced. 1 going to 0 is 1 electron, but for 2 hydrogens doing it, it's 2 electrons. See how we get the same number of electrons? as we did before, so there's nothing to worry about. So 2 times 3 here gives 6 times 2. Transfer the 2 and the 2. I'm going to transfer the 3 on this side. Remember, I'm not transferring it on that side because this side has to be balanced by inspection because there's H with a +1 here and H with a +1 there, meaning it's split amongst those two places. Okay, so at this stage, we would be ready for doing it by inspection. So what that means, I have this whole side, I have to adjust both of these numbers to get them to match the other side. So this could be a bit tricky, and the reason for that is because there's hydrogen and oxygen in here, and hydrogen and oxygen in the hydroxide, which means when you change one number, it affects the other number, and so that could make it a little trickier to balance by inspection, but it's totally doable, okay? So you would do 2 times 4 is 8, plus 3 times 2 is 6, so we know you have 14 H's, and you have to get this combination of numbers to add up to 14. While balancing the oxygen. It's a little tricky, but I'll show you a little tip. Right now, the charge isn't balanced, and there's only one thing that's affecting the charge, which is the thing we have to find the coefficient of, hydroxide. Water's neutral, aluminum's neutral. On this side, this whole compound has got a -1 and hydrogen's neutral. And we know the coefficients on the product side are done. We're done with those. So we know the product side's charge adds up to -2. So we can use the fact that a reaction has to balance for charge by getting more of the coefficients, particularly since we're missing the one that has one for the substance that has a charge. So we know that aluminum and water are neutral, and so they're not going to contribute to the charge. So if we want the left side's charge to equal the right side's charge, this has to be a 2. See how easy that is? We get to that number much more easily. And then we just have to figure out how to get this number. And so again, we count up the number of hydrogens, and we see that this has to be 6 so that they add up. So either way, it doesn't actually matter who you connect to. I wouldn't connect to something that's that you're already connecting to, to the species that has been oxidized or reduced, like we had in the other problem. I didn't connect to lead sulfate because it was already like participating because of the sulfur. Here, neither hydroxide or H2O is participating with aluminum. The aluminum is changing, but we've captured it with the aluminum hydroxide here, right? And it doesn't appear anywhere else. So the oxidation of aluminum is irrelevant. So in that case, it doesn't matter who I pick. And I just showed you how to do it either way, okay? It's obviously easier the first way because we get that 2 more easily, but if you know that little trick with charge, it makes it a lot easier. Okay, that's it. Thanks, guys.